Imagine an object accelerating along a track. Now, stop the clock. If you need to isolate exactly how much ground that object covered during a single specific interval, say exactly the 5th second of its journey, how do you calculate it? We want the distance covered in only this distinct 1-second window. We do not care about the first 4 seconds. Must we map out the entire history of the object's movement from the starting line? Or is there a direct mathematical shortcut to bypass the past? In classical mechanics, the standard equation for displacement is S equals ut plus 1/2 at squared. This formula is robust, but it calculates the total cumulative distance traveled from time zero. To find the displacement for just the 5th second using this standard equation, you have to run a grueling multi-step process. You calculate the entire displacement up to 5 seconds. Then you calculate the total displacement up to 4 seconds. Finally, you subtract the two totals to find the difference. In a high-pressure competitive exam like the JEE, this traditional subtraction method is a liability. It eats up precious time and forces you to execute multiple arithmetic operations, like squaring numbers, multiplying complex fractions, and subtracting totals, each one introducing a new opportunity for a calculation error. To build a better tool, we need to strictly define our terms. Mathematically, the nth second refers exclusively to the duration occurring between time equals n-1 and time equals n. Conceptually, isolating this gap is an exercise in subtraction. This timeline illustrates a complete journey. Here is our total displacement up to time n, and here is the total displacement up to the start of our target interval, time n-1. Subtracting the earlier journey removes the object's history entirely, leaving us with our exact target value. By performing this exact algebraic subtraction in advance, we can condense the process into a single formula. We can skip redundant quadratic math and jump straight to the interval we actually care about. The formal setup for our algebraic shortcut is Sn equals Sn minus Sn minus 1. When we expand the polynomials for both terms, the heavy quadratic elements emerge. But because we are subtracting the two equations, the massive un and 1/2 an squared terms mirror each other. They cancel out entirely. The math collapses into a remarkably clean result. The displacement in the nth second equals the initial velocity plus half the acceleration multiplied by 2n minus 1. At this point, top-tier students usually notice a glaring dimensional paradox. On the left, we have displacement, measured in units of length. On the right, we are apparently adding initial velocity, length over time, to acceleration, length over time squared. By the strict rules of dimensional analysis, this equation should be impossible. This table resolves the paradox. The derivation relies on a strictly bounded gap of 1 second. Because delta t equals exactly 1, the variable t effectively vanished from the visible algebra. We are implicitly multiplying the velocity and acceleration terms by 1 second, canceling out the time dimensions to yield pure length. The formula operates perfectly. It represents a precise, dimensionally sound rate of displacement per unit second. Let's measure the efficiency gained here against a standard kinematics problem. A body starts from rest, meaning initial velocity is 0. It accelerates at 2 meters per second squared. We need the displacement specifically in the 5th second. The traditional method requires computing 5 squared, computing 4 squared, having the acceleration, and subtracting 16 from 25 to get 9 meters. Using our derived formula, we plug in our values. The initial velocity drops to 0. 2 over 2 is 1. 2 times 5 minus 1 is 9. 0 plus 1 times 9 gives us the 9-meter displacement immediately. The mechanical advantage is absolute. The formula turns a multi-step, error-prone quadratic calculation into a single linear arithmetic operation. Under exam conditions, those saved seconds compound into higher scores. When we shift this geometry to vertical motion under gravity, the specific boundary conditions simplify the math even further. In an ideal freefall, an object drops from rest, and the acceleration is a constant 9.8 meters per second squared. Because initial velocity is 0, the u term vanishes. The shortcut formula collapses into a purely linear relationship. Displacement is proportional solely to the factor of 2n minus 1. Over 400 years ago, Galileo Galilei observed this exact pattern. This historical table illustrates his findings. The distance an object travels during consecutive equal time intervals follows the exact sequence of odd numbers. If we substitute n equals 1, 2, 3, and 4 into our collapsed formula, our algebra perfectly reproduces Galileo's physical data. We generate the exact 1 to 3 to 5 to 7 ratio of displacement. Galileo mapped this reality empirically, using smooth inclined planes to dilute gravity and slow the acceleration enough to measure the intervals with a water clock. Our formula exposes the underlying mathematical architecture of his discovery. While the total displacement of a falling body grows quadratically, the incremental distance covered in each new second grows linearly. That linear expansion in interval distance is why an object appears to pick up speed so aggressively as it falls. The nth second formula is a high-precision tool, but if you apply it without verifying the boundary conditions of the system, it will systematically output the wrong answer. The primary conceptual trap lies in the definition of the variables. The formula solves strictly for displacement, a vector quantity, not total distance traveled. Consider an object thrown vertically. This diagram tracks its trajectory. It reaches its maximum height exactly 2.5 seconds into its flight. If an exam asks for the distance covered in the third second, the interval between 2 and 3 seconds, we hit a critical boundary. Inside the specific 1-second window, the object moves upward for half a second, stops, and falls downward for half a second. The positive vertical gain is perfectly countered by the negative vertical drop. Because displacement measures the net difference between the starting and ending positions, our formula will yield 0 meters. The total distance traveled, however, is the absolute sum of those two phases. Failing to check if velocity reaches 0 within your target interval is the single most common cause of lost marks on nth second questions. The second major constraint is the nature of the acceleration itself. The formula requires constant acceleration. If acceleration is a variable function of time, for instance, a equals 2t, the algebraic shortcut breaks entirely. The derivation assumes the average velocity over the 1-second interval is simply the arithmetic mean of the initial and final velocities. In a system with variable acceleration, that mean no longer reflects reality, and the interval must be integrated using calculus. Conversely, if the constant acceleration is negative, acting as retardation, the formula holds true, but the displacement calculated per interval will incrementally shrink until the object's direction reverses. When deployed correctly, the nth second formula is the ultimate analytical shortcut. So long as the acceleration is uniform and the vector direction is verified, it cleanly steps the quadratic histories that bog down traditional calculations. It isolates a single piece of the kinematic puzzle, proving that mathematical efficiency comes from knowing exactly what variables to discard. You do not need to track the entire history of an object's motion to understand its current behavior, because sometimes the only thing physics requires is the data from one exact second.